organizers, and so yeah, I want to talk about universality of free random variables. So free probability theory, we have this notion of freeness, we are talking about free random variables. And the idea is that freeness is a kind of special situation. If guys are free, it is very special, and important and universal. And in principle, we should be able to compare general situations with the free situations. That's what I want to do. I want to give an idea that free variables realize, in a sense, extreme situations compared to other variables. Okay, so maybe the setting. So this is a Riemann algebra setting, and it's important it's a finite setting. So we have a trace. Otherwise, not have freeness. Not with respect to trace, but I mean here it's really important to have trace. Also the setting is I have non-commutative W-star probability space. This just means that M is a Riemann algebra and how is it trace. So I'm really looking on a finite Riemann algebra. Okay, and then I want, and I mean this M, I mean I have variables. I'm not really interested in Riemann algebras, I'm interested in variables or operators who live in some von Neumann algebras. So I mean, von Neumann algebra, they live, and it's not important, it's just that it's a type finite setting. No? Maybe I can have a very big von Neumann algebra where everything lives. No? Good. Okay, so what I want to consider, I want to compare tuples of operators, and one tuple should just be general operators, and the other tuple will be a free tuple where the elements are free. Oh, okay, so that will be my setting. So I look on variables, general ones, I denote them by y. So I have, let's say, d of them, d tuple, guys, by 1 up to 1e. So this is a general tuple of operators in such a setting, and I will in the following always assume that my operators are self-adjoint. Some things can be done in general, but maybe it's easiest to talk about self-adjoint ones. And I want to compare this with a tuple of free variables, and the free guys usually I denote by x. So those will also be operators, but they are more special because they have freeness in themselves. So this is usually free. And even if you don't know what freeness means, it's a special situation which you consider free probability theory. Okay, but maybe one, so what is the question? I mean, what I want to compare, somehow, I want to compare a distribution of such a situation with a distribution of this. Okay, distribution, okay, it's maybe a tricky thing. So what we usually do is that I apply polynomials to my operators, let's say self-adjoint polynomials, so that I get a self-adjoint operator. And if I have one self-adjoint operator, of course, then I can talk about this distribution, and I have a lot of tools for doing this. So what I want to look at is a non-commutative polynomial in d variables, so that I can apply it to my tuple. But of course, I mean, I want to do this for all polynomials. Not fixing a polynomial, but making statements about arbitrary choices. But let's say also say it should be self-adjoint. So this means that if I apply this polynomial to self-adjoint operators, the output is also something self-adjoint. Okay, and then I want to compare the application of this polynomial to y's, general operators, and the polynomial to the x's. So I want to compare this polynomial applied to y, yd. I want to compare this with the same polynomial applied to the x's. Good. Okay, and of course, I mean, what do I mean with this compare? No? Of course, what I really want to do and what we can control is actually the size of the eigenspaces of those guys here. Or maybe in a more distributional way, I mean, if I have tau and I have a self-adjoint operator, then I have a distribution of this, which is a probability measure. And what I can look at are the atoms of this probability measure. And this really corresponds to the sizes of the eigenspaces of those guys. So I want to compare the size of eigenspaces in the general situation with the size of eigenspaces in the free situation. And the idea is this here should be an extremal situation, and extremal means, and it will mean that actually the sizes here are the smallest possible, and everything else must be bigger. Okay, that's Yeah, okay, but maybe for this, let me first say what we're looking at. I mean, the sizes of the polynomials. So maybe here I have such a P, a Cebron operator, which in our case will come by applying the polynomial to the given ones. This is of course something which lives in my Neumann algebra. And for this, I'm looking on, let's say, a discrete measure, which gives me the eigenvalues and the size of the corresponding eigenspaces. So for this, I look on discrete measure, which I denote by mu. Then I have P, so P is my operator, and then I put here A for atomic or discrete. So it's just an atomic part. In general, I have a full distribution of this, but I'm only interested in the atoms. And so this puts on lambda the mass of the size of the corresponding eigenspace. So I'm looking on the eigenvalues and the eigenspaces, and they have a size. Okay, we have infinite dimensions usually, so the size of this eigenspace is measured by tau applied to the projection into the space. So it's something between 0 and 1. So this is tau of the projection onto the eigenspace of the eigenvalue lambda. So this only puts mass on the eigenvalues. Okay, so if you want to talk about the distribution of our operator, which is just a probability measure, then this is just picking out the atoms of this one and ignoring the rest. Good, okay, so this is a discrete, let's say, sub-probability measure. Of course, the total mass doesn't have to be 1. And so my question now is, can I compare the size of the eigenspaces here with the sizes here? And of course, I mean, I need some input. I mean, the y's and the x's should somehow have similar behavior with respect to this. So what I assume is that the size of the eigenspaces of the y's is the same as the size of the eigenspaces for the x's, for each of them. Okay, and then I want to see how big is the size of the eigenspaces here compared to this. Okay, so I assume I'm given, and maybe another way, I can just say I'm given this size of the eigenspaces for each y a for I. So the question is, what can we say about the size of the eigenspaces for any polynomial in the y's? So the mu of polynomial y1 up to yd. Okay, and of course, I mean the atoms which I get in polynomials, then they come somehow from the atoms which I have in the individual variables, and also from some relations between the variables itself. Okay, and I mean free variables, this is a situation where I'm eliminating all non-trivial relations between the variables. So this is a situation when the polynomials, only the atoms in the variables themselves should show up. And actually the idea is, what you see in a free case is something which you should see always. So I mean, in general, of course, you might have more atoms, and you might have bigger spaces, a bigger size for eigenspaces than in the free case, but at least what you see in the free case, you must also see in general. Okay, and that's our theorem. So let me write this down. So that's the main statement. Give you some idea where this comes from. The most important part is the statement, which is coming now. So this is this is joint work with Octavio Arizmendi, Roland Cebron, and changing. And so this is the way we decide this paper, which is from last year. Okay, and so maybe let me report again the situation. So I consider y's, y1 up to yd, which is an arbitrary tuple, always in a finite algebra, and I compare this axis, which is a free tuple. Okay, all of them are self-adjoint. Okay, and now I assume that individual variables, the y's and the x's, have the same atoms, the same eigenvalues and the same sizes, the eigenspaces. So this means that mu of yi is the same as mu of xi for all I. So this means the atoms and their sizes, so the weights are the same for each of them. And then the statement is, the conclusion is, that then if I'm looking on a polynomial, then if I'm taking this polynomial in the y's, y1 up to yd, looking on the atoms, this is always greater or equal than the atoms of the corresponding polynomial in the x's. Okay. And so this means that whenever I have an atom here, I also have an atom here, and the weight of this atom is greater or equal than this here. That's what this here means. And this is true for all polynomials. I mean, we are not talking about special polynomials, but it's really a general statement for all self-assured polynomials. Okay, and I mean, you can also, instead of saying here you have equal, you can also start here by having something which is bigger, and then bigger will survive here. Okay. So maybe that's actually what you're proving in this object. Good. Okay, and a corollary of this, or maybe a part of the proof, is actually that the atoms in the free situation, which you get in the free situation, only depend on the atoms of the individual xi. And not on the rest of the operator, not on the rest of the distribution. So this is, maybe it's included in this theorem, but at least it's an important part in the proof. So in the free situation, because you can apply this also to y's, I mean, you can also choose them free, but then only the atoms have to be the same, but the rest you can change, and then you have this in both directions, which means it's equal and the rest doesn't play a role. Okay, so it's a corollary that the atoms for polynomial in free variables, and of course, I mean, that's what you're interested in free probability theory. You want to understand distribution of polynomials or some functions in free variables. We want to see how is it given in terms of what we know about the x's. And here we have a very precise statement about the atoms. Also, the atoms in polynomials depend only on the atoms for the individual xi. Okay, and not the rest. So usually we have variables which have some atoms, and of course they have some less. Good. Okay, so that's the statement. I hope this is clear. Okay, and then the rest of my talk is just giving some high-level idea how to prove this, or where this comes from. Okay, and the main idea in this context is that actually, I mean, having an atom is something which can be detected or controlled algebraically. Of course, we are here in an analytic setting, we have operators and polynomial algebras and so on, but atoms is something which has a very analytic flavor, and of course, it's really, it's essentially an algebraic situation which we're looking at. So in particular, atoms can be detected algebraically, and it also, I mean, it's really about talking about the inverse of operators, checking whether inverses exist, but you have to be careful. I mean, of course, I mean, the inverse of an operator cannot exist because point is in your spectrum, but then this means it doesn't exist as a bounded operator. If you allow unbounded operators, then it's exactly the question about the atom, whether the inverse exists or not. And that's why we are in a finite setting. That's only true in a finite setting. Okay, so I mean, the fact that P has no atom at lambda, so this is the same as saying that P minus lambda is invertible, but not in my polynomial algebra, but as an unbounded operator. And the affiliated operators affiliated to the polynomial algebra, and because we are in a finite setting, these affiliated operators are really nice. They really from the star algebra, so they really behave like, from a finite dimensional situation. Okay, so P minus lambda is invertible as an unbounded operator in a finite polynomial algebra. Okay, and this means what we want to look at somehow are minimal situations for the y's. And at the moment I'm forgetting about the free situation, but I'm going more into an algebraic direction and try to model the minimal situation, or what you always have in such a situation where you are giving the marginal distribution of the y's, how to model this in an algebraic way. Okay, and actually you can realize this situation by the so-called free field and matrices over them. Okay. The free field, this is an algebraic notion. I mean, it should be called a free skew field, of course, it's a non-commutative field. So this is, maybe, so this is C. We first write down the notation, C in 1, up to 1D. These are sharp at the angle bracket. So this is the notation for the free field, besides the free skew field, which is or are non-commutative rational functions in formal variables y1 up to yd. So those are non-commutative rational functions in formal variables y1 up to yd. So you take the free algebra, just non-commutative polynomials in the y's, but then you also go over to taking inverses. So I mean, this free field is whatever you can get by taking plus and times, but also inverses of all your variables. Okay, you can always invert things unless they are zero. So it's really a field. Okay, I mean, that such a thing exists is not trivial. I mean, this is, in the commutative case, of course, you just take the fractions or your polynomials, the rational functions. But here, in the non-commutative, it becomes more complicated, but this thing exists. So this is considered in algebra, and I mean, 50 years ago, so there's a long history of this. It's a very nice object, and it can also be realized in terms of linearization. I mean, that's how we make contact to this. But anyhow, this exists, and in principle, this is the algebraic object, which represents universal variables which have no atoms. I mean, the y's here are invertible. Everything you can build of the y's is invertible. So this really means the y's is the algebraic avatar for operators which have no atoms in their distribution. Okay, but now of course we want to look on situations where I have atoms, but this you can realize in this setting if you go over to matrices over those guys. Because then if you have matrices, you can produce atoms by the matrix structure. Okay, so going over to matrices, over the free field, you can also deal with kind of universal objects where I can prescribe the atoms. Okay, so maybe let me just describe an example what we have to do. So I'm trying to create something of which every tuple of operators which have a given marginal distribution is a specialization. Okay, good. So I want to realize, answer the question, what can I see in any P of y in algebraic terms, and then later I will say why I can also go over to the free variables. At the moment, I mean, freeness in the sense of free probability is an analytic notion. No? Okay, so now I'm going to an algebraic setting. So I want to, let's say I want to consider two operators, y1 and y2, where I prescribe the marginal distribution, and then let us try to realize this situation in this free field, or matrix for free field. And of course, I mean, if I have n by n matrices, I cannot create only atoms which are the weight is a multiple of 1 over n. Okay, so it really it's only for rational weights that I can do this, but again I can approximate everything by this. And so maybe let me take a situation where the atoms have weight, let's say 1/3 or so that I can do this in 3 by 3 meters. Okay, so. Yeah, so let me say I have one operator, y1, whose size of the eigenspaces, or let's say who has eigenvalues 1 and 2, and the size of the corresponding eigenspaces is 1/3 and 1/3. So this atomic distribution here is 1/3 delta 1 plus 1/3 delta 2, and of course then there is so this is at 2, and then there is a part of the operator which has no eigenvalues, so which also has mass 1/3, but which is not really important for this. But of course I have to model it somehow, but things which don't have atoms are modeled by elements in the free field. So this guy here can be realized in the free field by a 3 by 3 matrix. Yeah, where I put just the eigenvalues which I have at 1 and 2, I put them there explicitly 1 and 2, and then the rest is just something which has no atoms, and this I model, let's say, by a variable y1 for my free field. Okay, so this is now an algebra, and in the sense, this, any operator like this is a specialization of this type. Okay, but of course this is just one operator. In general I have more, and then of course non-commutativity plays a role. I have to be more careful. So maybe, so let's say this here lives in the 3 by 3 matrices over the free field in just one variable. Okay, but now if I also have a second operator, and let's say this has eigenvalue 4, again with size 1/3. So also sitting on 2, then the atomic part is just eigenvalue at 4, this mass 1/3. And then of course, if I only would have this, I could realize this in the same way by taking the variable where I'm putting the 4 here, and then I have the rest has no atoms, and so this is represented by just some other variables in the free field, so that we call them y2 and y3. Okay, so this is now an operator which has an atom of size 1/3 at 4, and the rest is just some continuous part. This realizes this. But of course now I want to realize both guys together, and of course I mean general y1 and y2 are not a specialization of this situation, because I mean this guy is diagonal, this is diagonal, so this would be a commuting, not really commuting, but it would be a special situation. So what I have to do, I have somehow to make this here generically rotated against this one, so that I really get the most general situation, and I can do this by rotating this here by a formal unitary matrix. So I use now, again, I use a formal unitary matrix, just invertible matrix, and again, to be as general as possible, this matrix should again live in a free field. So the entries of this are also just elements from a free field. So I'm taking here now variables u11, u12, u21, u23, and so on. And here I'm putting the inverse of this. And this is now what I call B. And this is somehow, I mean, this is now, so this should be unitary, just invertible, this setting be enough. So this is then operator, which has this distribution, but if I now take it together with this A, this should realize in an algebraic way the most general situation of y1 and y2 is this given distribution. So this here is a formal unitary, let's say, matrix. And this is invertible, so this exists. And actually, so now the U's are also just elements in the free field. So I'm now in the free field where I have, if I look on everything, I have the y1, the y2, and the y3, and I have all these U's. So all those guys are variables in the free field. And of course, I mean, this matrix is invertible in the free field. And actually, entries which I get here are now really rational functions. I mean, up to now, I only talk about polynomials. maybe you haven't seen rational functions, but here they really show up explicitly. Because I mean, if I take the inverse of a matrix, I get a rational function in the matrix. And that's true in general. So in the free field, I mean, such matrices are invertible in the free field, but of course then you get a matrix where the elements are rational functions. They're not staying in the polynomials. Good. Okay, and now, so what I have now is now A and B. They live now in this free field, and actually right now I'm interested in a polynomial in, let's say, y1 and y2. I can realize this by looking at a corresponding polynomial in this A and B. And this should contain, this gives me the minimal possibilities for the eigenvalues and the eigenspaces. So A and B, and any polynomial in them live, of course, now in the 3 by 3 matrices over all the variables which I have there. So these are the 3 by 3 matrices over the free field of y1, y2, y3, and then I have all the u's, v1 up to 3. Okay, and this means if I want to calculate the kernel of such a polynomial, of course, the only, for any size of any atom, the size of it can only be a multiple of 1 over 3. So this shows particular the sizes which you can get here, of course, are related to the sizes which you get to the size of their kernels. Okay. The size of A and B, the kernels we know, but for polynomials can only be 0, 1/3, 2/3, or 3/3, and actually this can be calculated in an algebraic way. So namely, I mean, if I want now to calculate, if I take now any polynomial in those guys, I will get a matrix in this. This is a free field, and the question is, I mean, can I somehow see what is the size of this? I mean, here you see by their eyes what the kernels and the sizes are, but if you have complicated expressions, maybe this is not so clear. On an analytic side, of course, we say, okay, we take the projection and we take tau, but in the algebraic setting, I don't really have. I have the tau, and the tau has been lost. I mean, I have the trace of the 3 by 3 matrices, but actually, of course, in matrices, you can calculate the size of the eigenspaces or so by looking on the rank. And actually, there's a rank in this setting, in a rank, which allows you to calculate those kernels. So those guys can be calculated via the rank, let's say the inner rank. Of course, I mean, the commutative setting, I mean, there's only one rank, but there are many ways of describing it. They are all equivalent. In the non-commutative, this is not necessarily true anymore. So, but what we take is the inner rank, which is really a algebraic notion. So namely, this just means if I have my matrix, let's say my matrix P, and let's say this is an n by n matrix, and where n is equal to 3. So what is the inner rank of this? This is the smallest number, natural number, such that I can factorize this P in terms of rectangular matrices, where one side is this possible rank. So this is the smallest natural number K, such that I can write P, which is a square matrix, as a product of rectangular matrices. So this is still n, but this here is K. And I want to make K as small as possible. And then this is the rank. So this is a number between 0 and n. I mean, for the 0 matrix, I declare the rank to be 0. Okay. Otherwise, it will be between 1 and n. And the connection between the distribution of my atoms is that actually this is more or less, it gives you the size of the atom. So namely, to move P atomic at, let's say, 0. I mean, if you're looking on the rank, this is really looking whether 0 is eigenvalue or not. So this is 1 minus K over The k is this one here. Okay, so this means we can calculate those quantities in which we are interested really in an algebraic way. Good, okay. And in this setting, now if I have now general y's, y1 and y2, then they are always a specialization of this a and b, and this means that they must have at least the atoms at places where the a and b have atoms. So I mean, in this setting, it is clear because I mean, y1 and y2 is a specialization. So I mean, whenever the y's are invertible, this means the a and b's must also be invertible. So whatever you have in the y's, so it's invertible, then it must be invertible in the a's and the b's. This means whatever is not invertible for the y's must come from the fact that it is not invertible for the a's and the b's. Good. Okay, so that's the algebraic setting. And up to this point, I mean, it's not really saying about free variables. But now, in the next step, we can now go back to an analytic representation. So what I have done here is I have a general analytic situation, and I say this can be represented by an algebraic setting where I can do the calculation in algebraic ways for the minimal ways. Okay, but now I say this algebraic situation is actually isomorphic to a special analytic situation which is given by free variables. And then I can really do, I can compare the general situation of operators with corresponding situation with free variables. So maybe you find that. Yes. Okay, and this then I can go to this specific analytic situation. I mean, this depends on work which I had done before, together with Tobias May and Chen Yin, where we looked on the situation where I don't have atoms, which means we are only looking on the free field. How can I realize the free field in concrete variables? And then we had an explicit characterization which tuples of operators realize the free field. In particular, it's tuple of operators which are free and have no atoms in their distribution. Okay, and so this is something which we can use here. So namely, I can then replace the formal variables, the y's which I use there, by free semicirculars, let's say. Semicirculars are the nicest operators, distributions without atoms. Okay, so this means building on this work of Tobias May, I said it can mean from 2019. We know that the free field can be generated as division closure of, let's say, free semicircular elements. And this means I can also realize now this A, let's say x1, which is now given by 1 and 2, and this formal variable y1 I can replace by a semicircle s1. Okay, and the B I can replace by, those guys are replaced by free semicirculars, and then, I have to think about what to do with the use. But at least, I can take here free semicirculars, 2 and S3. Okay, and for the use, I could just take also free semicirculars for them, but then I would not get a unitary. I would get something invertible, but not a unitary. And what I really want is that I want to make those guys to be free, and for this I have to choose those guys in the right way. So namely what I have to take here is I have to take a high unitary, which is given by free compressions. Also the elements which I write here, U11 up to U33, I'm not choosing them free, but I'm choosing them by free compression of a high unitary. And then one really has to work to see that the U's which I get here are still realizing the free field of the U's which I have in this general setting here. So that's part of the main work, really, to get this in a way that actually, I mean, I get here something which realizes the situation which I have in the free field, but in addition, I mean, this x2 and this x1 are also free among themselves. Because only then I'm in a setting where I can use free probability theory. Okay, but in any case, from the results which we have here, it follows that this can be done. But this is, yeah, a bit more work, so I don't want to go into this, but at least the division closure of the operators, which I'm using here, maybe let me call them here util, because it's concrete operators, those here are the formal variables, so of all the guys which are here, S1, S2, S3, this is really the free field of the formal variables which I used before. Let's say 3, 1, 1, 2, 3, 3, and y1, y2, y3. Yeah, okay, so this means I have really here an analytic model of what is happening in the free field, but in this analytic model I really have achieved that I really have free variables. And I mean, of course, each of them has exactly the atoms which I wanted them to have. Okay, but I also have somehow brought these atoms in a generic situation by doing here a kind of random rotation, but I mean it's a rotation which I can control, which is generic, but in a sense analytically makes those guys free. Yeah, and then if I have this, then this means the calculations which I'm doing for the free operators really gives me the same atoms as I have in the algebraic setting, and with algebraic setting I could compare with general setting. So I mean, so I achieved in the end what I've done. So I mean, I have a general analytic situation. And I want to make statements, so those are the y's. Now let's say I want to do this situation, I have y1 and y2. So I compare this to an algebraic situation, which is given by these operators A and B, such that any such situation is a specialization of this, and this means that the atoms which I see here must also show up here. So this gives me exactly this comparison, that the atoms which I have here for y1 or for any polynomial, y1 and y2, I must also have on this side here, of polynomial b. And here I'm calculating in algebraic way, so this is really coming from the inner rank. So this here, so this is actually an algebraic computation, but which corresponds to looking on the size of the eigenspaces. Yeah, okay, and then the next step, which I just explained a bit, is that this algebraic setting is actually isomorphic to an analytic setting which is given by free variables. So I have here a special analytic setting, namely the free one, which is given by operators x1 and x2, which have the same marginals as VAs, the y's. Okay, but those guys are free among each other. Okay, and then based on these results by Tobias and Cheng and myself, I mean, I can see that actually this here is really the same as what we have here. So this, I mean, this is not just a specialization of this, but this is really isomorphic to this thing. So this is really the same as calculating polynomial x1, x2, and the atomic part of this. Good, okay, and so I mean in the end, you get this comparison here. Because I mean, if you really want to do calculations, I mean, of course you can say I can do these calculations here with the inner rank, but of course this is getting very complicated. In principle, maybe there's an algorithm for doing it, but I mean here, for free variables, we have more analytic tools for really doing calculations. So one point is that you can use what we know in freeness to give somehow lower bounds for what can happen in the general situation. But of course, this comparison also allows you to get results about polynomials in free variables. And of course, I mean, if you want to know what are the atoms in a polynomial of free variables, okay, where you prescribe the atoms for the axis, and then you can find a general situation with the prescribed atoms where you don't see an atom in this polynomial, then you know there can be no atom on this side. So this means you really can exclude by choosing maybe here realizations of a situation. I mean, you want a free situation, but I mean, for atoms, maybe you can exclude many things by looking on easier situations. Even if you take the device commuting, this might give you some interesting results. Okay, and so maybe I mean, for the free probability community, it's also important that from this you can get quite a bit of new results on atoms in distributions of polynomials in free variables. Okay, so and for example, one direct consequence of this, namely if you realize a given distribution by diagonal matrices, then you see if you apply a polynomial, then you can only get atoms at positions where you apply the polynomials to the eigenvalues of the separate lambdas. So this means the possible positions of the polynomials in your free variables can only occur at positions which are the polynomials of lambdas, where lambdas are the eigenvalues of the variable itself. So I mean, this is a non-trivial statement, which is not, I don't know whether this can be proved directly in any other way. Also, maybe that's one easy to state consequence. So the only possible locations of atoms for polynomial x1 up to xt in free variables. For general variables can have many more atoms, but for free variables, these are only positions where I apply this polynomial to eigenvalues of the corresponding axis. So lambda 1 up to lambda p, where lambda I is an atom, possible atom of xi. Okay. And I mean, we can also make statements sometimes about the size of the size there. I mean, there's no general formula for all, but in many situations we can be very precise, and actually one can really give equivalent characterizations. Okay, and I mean statements like this in free probability, a lot of this was done for the sum, for the free convolution. So when can we have an atom in the sum of two free variables? And one of the main results there was that actually you can only have an atom at a position lambda 1 plus lambda 2, where lambda 1 is an atom of the first variable and lambda 2 is an atom of the second variable. And you can really say exactly what the sizes are. The atoms must be big enough. The sum must be bigger than 1. And I mean, this you can recover from this here. And you can also, look on the commutator and anti-commutator and recover known results, but also go further. And actually, you can also, for more general polynomials, so big classes of polynomials, you can make very precise statements. Good. Okay, so that's okay. Say more about this. So we have kind of formulas for calculating sizes or giving a lower estimates for the sizes. But anyhow, so I think that's more or less what I wanted to say. Maybe I should say that, I talked here about self-adjoint polynomials, but this can be, or self-adjoint operators, this can be extended to normal operators. And of course, the rational functions showed up here, but maybe only in the course of the proof. I started by polynomials, but of course, instead of applying polynomials to my operators, I can also apply rational functions to my operators, and the same kind of statements are true there. So instead of taking a polynomial in my statement here, I can also take a rational function And then again, the free situation realizes the extreme situation here.
You mean, I guess you have to assume that the yi's are in the domain of rational?
Yeah, I mean, you need that they are in the domain, no? And then the x's are automatically in the domain. Yeah. Of course, you only can look on rational functions which you can apply. That's always with rational functions. In the free field, you can always apply them to from the variables, but for complete operators, of course, very often you have, even if you don't have polynomial relations between them, you have rational relations between them. So you must assume that you're looking on a situation where a rational function can be applied. And then this statement here is also true. Good. Okay, so I think I will stop here.